Hello, in the previous videos of this series, we have explored the endpoint green functions of a field theory in a non-perturbative way. Right? We got some pretty neat results, the spectral density. We proved that there are poles in those green functions every time some internal or external momenta go on shell, and those are all very interesting results about the behavior of these endpoint green functions. But we know that most of these quantities that we have discovered along the way, like this Z, the spectral density itself, the position of these poles, right? They are very hard to calculate non-perturbatively. It's not impossible for some theories, but very hard, right? And most of the important important comparisons between quantum field theory and experiments happened in the perturbative regime, where it's much easier to get these results and get good comparisons. Right? So now what we want to do is actually go and look at perturbative weakly coupled theories, right? And expand the series to compare with those general results and see how these perturbative expansions look for the quantities that appeared in the relations that we found in the previous videos. We're especially interested in the question that I alluded to in the very first video, which is how do we compare these quantities, take for instance the physical mass, with the parameter m in the Lagrangian, right? We call m0 now. Right? And that will lead us to the field and mass renormalization of quantum field theory. Right? So just to start, let's focus on a very simple case, which is a 2-to-2 scattering, or a 4-point green function. Right? We know that in the momentum space, this can be written in this way. I'm using the same conventions I had for the LSZ reduction formula last video, right? So I'll call xi the outgoing positions here, and p the outgoing momenta, and I'll call y the nk the incoming momenta and positions, right? And this is the matrix element I'm looking at: phi of x1, phi of x2, phi of y1, phi of y2. Right? And again, I'm still looking only at a scalar theory, because most of the complications that come from higher spin theories are just generalizations of the concepts we'll find here. So we will get to that eventually. Now, anyone that has done calculations beyond leading order in perturbation theory knows how complicated diagrams can get. I mean, don't mind the complication on this one. You would have to go really far in the perturbative series to find something like this, and I hope nobody ever has to calculate something this complicated. But it does illustrate a point I want to make here, right? We can actually take an arbitrary diagram in the perturbative series for this 4-point function and do a division that will apply to all of them, right? So what we have to notice here is take this momentum k1 going in here at this point y1, right? It runs through this first propagator here, and then the moment I have a vertex, I don't have k1 in the propagators anymore, because now there's a loop here, right? I'm integrating over momenta for that loop, over momentum on the loop. So each of these legs will have K1 plus the momentum running over. So K1 will be divided here somehow. But over here, if I look at this specific point right here, I have K1 again, right? So I have K1 flowing here again, just by conservation of momentum, right? If I compare this point and this, you conclude that whatever happens in the middle, I'll have this momenta running in a propagator again. Same thing happens for the other momenta I have drawn here. For instance, P1 is flowing again right here. P2 is flowing again here, right? And K2 does not appear again. I would have to put a division right here. Right? What I'm getting at here is that you can always, no matter how complicated the Feynman diagram is, you can always get a division between something that is intrinsically in the middle here, involving a combination of the external momenta, and something that is only a function here of these one of them, right? So essentially, you can make a division where you write a full connected diagram in terms of something that is a core here, which you call the amputated green function or the amputated diagram, right? And these these corrections to the external legs, which we call full propagators or dressed propagators, you name it. The point is I can divide corrections to the interaction itself and corrections to these propagators. And in this video, I want to focus on this part, on these corrections for the propagator. Now, if I write the perturbative series for one of these full propagators, it will look like this, right? So we'll have the free propagator, then some one loop contribution. Here I'm just using any theory. Say this is looks like a phi3 theory, but the specific interaction does not matter for what I'm about to say. So all the results are general. I'm just drawing phi3 because it's easy, right? There are more contributions that look like this, right? Say that this is another one loop contribution for phi3, right? And then you start having two loop contributions, so this is already a higher order correction here. And then of course you have diagrams that are very similar to repetitions of these loops combined, right? So you could have something like this, for instance, or at even higher order you could have, I don't know, something like this, right? And the thing is, I want to reorganize this series. And the nice thing about it is that I can basically divide these into three types of diagrams. One is the free propagator, right? Which is a thing on its own, right? As far as the loop corrections go, there are two kinds of contributions. So if you look, I have things that are just like basic elements, like these one, right? And I have repetitions. For instance, this guy is repeated here and here. And these two parts are connected by one propagator in the middle. Same here, right? This is just a combination of this guy and this one, right? And that leads to a classification, right? I'll call these guys that I cannot, and here's the important part, I cannot separate this internal part here, this diagram, into two by cutting just one propagator. If I cut this propagator, there's still one connecting both ends. If I cut here, there's still another, right? Same goes here, right? I cannot separate x1 from x2 here just by counting one propagator. If I separate the loop, this is not a contribution to the 2-point function anymore, right? And same here. These guys I'll call one particle irreducible diagrams. That means I cannot reduce them to a smaller diagram, smaller 2-point diagram, by just cutting one line. Right? These guys on the other side, which are combinations of these 1PIs, right? These and these, right? I'll call one particle reducible diagrams. The point being that these diagrams, right, have a 1PI diagram here times the Feynman rule will be this 1PI diagram times a propagator times another 1PI diagram, which means that if I cut this propagator or just remove this propagator from the Feynman rule, right, I'll have this product of two of these 1PIs. So the reducible diagrams can be reduced to 1PI if I cut the intermediate propagator here, right? So now if I define the sum of all 1PI diagrams, let's call that minus I, this is just convention, right? Same thing with this m square. Sometimes you see this being called m, sometimes sigma. I'll use sigma for fermions, for instance. But for now I want to use m squared because of the dimensions of this thing, right? You see pretty soon. This is a function of p squared, and I define this guy, right? This is the definition here, as the sum of all 1PI diagrams, one particle reducible. Let's put it in blue. Let us put that in blue because that's what I'm using here. Right? Of course, this is not the same as the full propagator, because if I take the sum of only the 1PI diagrams, I'm missing the free propagator, and I'm also missing all the 1PR contributions. But the point is that I can include the 1PR contributions, right? So the sum of all the 1PR contributions is given, right, by this plus something like this, right? This already includes these two that I have shown here. And of course, there's more. If I continue including something like this all the way to infinity, infinite number of 1PI bubbles like that, right? I'll have included every loop in my theory, right? Because I can just, what I'm doing here is just reorganizing my sum. Now, instead of this expansion being on the coupling constant, so here I have coupling constant square, also here, already here is coupling constant to the fourth, same here, I don't know, even bigger here, right? Here, each of these bubble has a full series on the coupling constant, right? Each of these guys, if I write it as a perturbative series, they will contain coupling constants, all powers, right? In this case, it's starting at lambda square, if I call the coupling constant lambda. This one is starting at lambda square, but that depends on the theory, of course, right? But all orders are included in each of these bubbles. And now I'm reorganizing the whole sum in this way, right? Where I have all the contributions that have just 1PI, the contributions that have the 1PI diagram, propagator, 1PI, and so on and so forth. Now, I can easily substitute all this part of this full propagator, right? This is the whole sum, right? Is equivalent to this whole sum. So the full propagator can now be written just as the free propagator plus all of these, right? So let's think of a scalar theory and start with the following Lagrangian. Say I take this Lagrangian, which is the simplest thing I can think of. And now I'll start calling this mass parameter in the Lagrangian M0, right? Because now we know that this guy is not necessarily the mass of a particle in our theory. And there is some interaction for this theory, but I want to keep this general. I won't need the specific form of the interaction for what I'm about to do. Right? And let's take a look at the 2-point green function, which is this full propagator, right? So d for x, omega t phi of x, phi of 0, omega, exponential of I px, right? So this is the full propagator. With momentum p. And I'll write this as this series right there. So you have the free propagator plus this whole expansion now reorganized in terms of the 1pi contributions. Now, if I want to write the analytics expression for this, right, I'll have to look at the Feynman diagrams for this theory, which we know, right? And this free propagator is just I over p square minus m0 square plus I epsilon. This I epsilon is not too important for what we are about to do, so I'll suppress it just to make the algebra cleaner, but I can come back with the I epsilons in the end, right? This is the first contribution. The second contribution, now I have propagator, 1pi, propagator. And remember, here I'm not just taking one 1pi diagram, but the sum of all of them, the whole perturbative series, right? Which I have defined by this minus I m square. And it's a function of the momentum going in, right? So I have the free propagator here, I p square minus m0 square. That sum of 1pi diagrams, which I'm calling here. I'll suppress the momentum here, but remember, this is a function of momentum, and a free propagator again, right? I'm summing all diagrams, right? There are 1pi, so this is in there, this is in there, if I have a lambda phi 3 theory, right? This is in there, all the way to very complicated diagrams. Now the next part is very similar to this one. Now I have propagator, 1pi, propagator, 1pi, propagator. So it's this times this, right? Propagator, 1pi, propagator, 1pi, propagator. And so on, right? I don't have to go much farther. I think everyone has understood where this is going. Now I can take this propagator and move it up front and write everything else in this way. This is 1 plus this plus this. This looks better, right? Which is, as you can probably recognize, a geometric series, the geometric series for this, right? This is 1, you have this element, then this element square, and so on, right? Which I can resum, right? Now, the whole series, right? So I'm talking about a perturbative theory, but I'm doing the resumation of the whole series, which is pretty neat. not always you can do that, right? So this will be just 1 minus m square p square m0 square to the minus 1. So this is divided by this thing inside the parentheses, right? Which I can multiply down here and get a very important result. So this is now an expression for the full propagator at all orders in perturbation theory. Of course, at any realistic situation, I will only be able to calculate this function of p squared up to a certain order in the perturbation theory. But the whole resummation of the series gets me this, which is a pretty important expression. What this tells us is that when we move from a free theory, which would have just this propagator with a pole in m0, right, and p squared equal m0 squared, right, to an interacting theory, you get this new contribution here, which obviously makes the pole position more complicated, right? And we call this function the self-energy of this field, right? And the reason we call this self-energy is because we're not even considering yet the fact that this particle, now that there is an interaction, it could be interacting with other particles. This is just a propagator. It's describing just one particle, right? What we are seeing here is that the very fact that the interaction now exists, right, is possible, right, creates this cloud of quantum excitations around the particle, which are essentially inseparable from that thing that creates it. The whole thing, particle plus cloud, is a dressed particle, is actually what we see, right? And this is what has a physical mass m and not m0, right? In fact, from our study of the spectral function, we have seen that the full propagator, which now I'll write in terms of this expression, with the self-energy here. If I go near the pole, so if I take P0 and take it near EP, where EP is defined by the relativistic dispersion relation with the physical mass, right? This full propagator will behave like something that has a pole in m squared, and now m is the physical mass for that particle, and with a different residue, which is this Z, plus finite stuff, right? Finite contributions, right? So it's dominated by this contribution, right? So we see from this expression that the self-energy has to move the pole, but also contribute to this residue that you have in the numerator here. We also know that with a simple field redefinition, I can get rid of this Z here in the numerator and get asymptotic states that behave just like the free theory, but with the pole in the physical mass. So let's do that field redefinition in our Lagrangian and see how this whole story changed if we do that. So I want to define a field, which now I'll name the renormalized field, right? Which is just given by Z to the minus half phi, right? And let's see what kind of havoc can we wreak in our Lagrangian by using this guy now, right? So the Lagrangian I had was just half del mu phi minus m0 square phi square over 2 minus v of phi. And I want to make this substitution here. Now remember that z is by construction independent of momentum or position, right? He was related to these element right here where I had boosted back to a one particle state of zero momentum and made a translation to the origin. So this is independent of momentum and of position, right? So when I substitute this z to the minus half here, it just passes through these derivatives and gives me just z over 2 del mu phi r del mu phi r. Here I get also again a z over 2. And I want also to write my Lagrangian in terms of the physical mass. So I'll make the following definition. I'll just write physical mass. Actually, this is not what I am defining. Physical mass is already defined as the one I measure, right? But this defines the following object. Right? I'll call m squared equal to m0 squared times z minus, and this is the thing I'm defining here, delta m squared. Right? This is strange to include, maybe strange to include z here, but if you think about it, when I use this definition, the consequence will be that m0 squared is equal to m squared plus delta m squared over z. And if I put this in here, m squared plus delta m squared over z, the two z's go away, and this term will be very simply written as minus m squared phi renormalized square over 2 minus this new term, which I'll call minus delta m squared over 2 phi r squared. So you have a mass term for the new field, which is very similar to what you had for before here, right? It's canonically written. And of course you also have, let's not forget this part, this becomes minus v of z half phi r, right? And which I'll also rewrite just to simplify the notation. I would just call it VR. So this is the renormalized potential of phi r, right? And of course, what happens in here, we'll see later when we take a closer look at the interactions. For now, there'll be changes there, but I don't need to worry about that, right? Now you see, I managed to write the mass term for this new renormalized field in a very canonical way. Of course, I get a new piece, but there is at least this, which is very similar to what I had before. And I want to do the same for the kinetic term, right? I want to have the kinetic term right in a canonical way. And that's, first of all, that should be possible because I know that this field has a very simple propagator near the pole, right? I already know that this field has a propagator which is just this, right? So it should be possible to do the same in the Lagrangian, right? And that's easy, right? I just have to sum and subtract the term I need. So I just add this thing. And then I group the subtraction of this very term with this one. So I'll get this half of z, which is just this term, right? Minus 1, which conceals this one that I added. Del mu phi r, del mu phi r. So I did nothing here. I just added up and subtracted the red part here, Okay? And then I just have to copy everything from up here. So just a moment. Phi r square over 2 minus del m square phi r square over 2 minus the potential. Right? And now, again, I will make a definition here, which is calling this guy delta z. So I'm making now this definition, z, which I have defined before, now will be written as 1 plus delta z. And this is the equation that defines delta z. Oops. Right? This is the definition for delta z. And in terms now of these quantities, I got a fairly simple Lagrangian, right? So I have half del mu phi r del mu phi r minus mass term m squared over 2 phi r square plus, let me write this in blue, delta z over 2 del mu phi r del mu r minus, now this part, del m square over 2 phi r square minus the interaction. Right? Now, the first thing to keep in mind is I didn't really add or subtract new terms to my Lagrangian. This is just a change in the variables I'm using to describe the same Lagrangian, right? I can just go back by making these substitutions, right? So this is really the same Lagrangian. I'm just writing it in terms of new variables. That's very important. Also, these can be separated quite easily in terms of a free Lagrangian, which I'll call L0, and an interacting one, which I'll call L1, right? The reason I'm including these delta z and delta m in the interacting one is that we know that in the free theory, z needs to be equal 1, right? And m squared needs to be equal to m0, right? Which means that in a free theory, delta z is 0 and delta m squared is 0. These two guys need to go to 0 as I turn down the coupling, whatever coupling is in here. So they are dependent on the coupling. So they are essentially only, they are part of the interaction, right? They carry information about the interaction, and in a perturbative series, they will be also a series in powers of the coupling, right? So that's why I'm including them in the interacting Lagrangian. Also, I call these terms here in blue counter terms, right? These are the famous counter terms of perturbation theory, which sometimes I see people, confused about, like thinking, well, you add counter terms to your Lagrangian, so you're really changing the physics. I hope this development I just did here shows that really the counter terms, they show up just as a result of a change of variables, right? I'm really not changing my Lagrangian, right? I'm still working with the same physics. Now I can look at this Lagrangian, right, and do a perturbative series on it, right? You have to assume that there is some sense in which I can expand on delta z and delta m. This is not obvious, at this moment, we'll get to a more strict definition on what exactly I am spending on here. When we, but for that we need a specific interaction, right? Specific examples. So for now, just keep that in mind. We are assuming it makes sense to spend on these guys too, right? When I'm spending the coupling constant, I will also spending on these guys. And then I can get Feynman rules out of these, right? So the Feynman rule that comes out of the free part of the theory is what we expected, right? There is a propagator with momentum p, and this propagator will be given by I over p squared minus m squared, because now this Lagrangian has the physical mass explicitly there. Bring back the I epsilon, right? And the interacting part gives us the following rules. Let me copy it because I'll have to go down for more space. So you have these two terms. So L1 is giving me, from this part, I have something like a 2-point vertex, right, which is proportional to delta z. Right? And of course, because of these two derivatives, there's two powers of momentum, p squared. And since we are in Minkowski space, there's also an I here. Right? And this part is similar, right? But now there's no derivatives, there's no momentum. This is just minus, because of this minus, I delta m squared. And I can group these two contributions here in these 2-point vertex, which will, again, for momentum p going in, right, will be given by I p squared delta z minus delta m squared. So this is the rule for this 2-point vertex. Of course, there's also something that should come out of the potential, right? So the 3 or more point interactions, right? But we are not worried about that now. We won't need these Feynman rules for what we're doing. Yeah? So now I can use these rules to recalculate the full propagators in terms the full propagator in terms of these new variables. So again, I'll be doing that series. We did all the way up there. This one. Let me go down. And this will now be, this is the full propagator, right? So the first term is just I p squared minus m squared physical mass now, plus I epsilon, plus same thing, the 1pi diagrams that come from here, minus I m squared. And we need to be careful with this m squared. It's not exactly the same function as before, because now it's written in terms of these new variables. But instead of just carrying a renormalized self-energy here, I'll just write it like this, right? Just to save us from too heavy notation. But keep in mind, now I'm calculating everything under these new variables. Right? And of course, again, I can resum this series and get to a very similar expression to what I had before. Right? Now with the physical mass here, and keep in mind that all these 2-point vertices here, I choose to include with the 1pi contribution. So even this diagram is considered under these, it's just choice I'm making, right? I'm considering this a 1pi diagram, So then you can have 1 PR combinations of this guy too, right? So now what I'm saying with this is that the 1 pi contribution, right, will be given by this plus a contribution that comes from loops. And I can write this analytically in this way. So let me take this in here and write it explicitly, right? So I call this guy minus I m square will be equal to this part, which is just I p square delta z minus delta m square minus I, and now this is again the same thing, the sum of all 1 pi diagrams, but only the loop ones. This is a new function. It's also both this guy and these are functions of momenta, of course. Right? Now, to make sure that I made definitions for delta z and delta m, right? But to make sure that they are doing their job, which explicitly means that this is the physical mass and the propagator of this new renormalized field behaves as in the free theory, I have to impose conditions, right? Conditions which are implicit so far. So I want to make these conditions now explicit through equations, right? The two conditions are these, right? So I want m to be the physical mass, which fixes the position of my pole, right? And I want to fix the behavior of this propagator near the pole, which fixes the value of the residue, right? This first one is very easy to implement, right? I just have to look at this expression up here, right? And say that p square minus m square minus the self-energy, right? If I look at this expression, when p square is going to m square, same number I have here, this needs to be 0, because then I have a pole for this function, right? Which gives me the explicit condition now that the self-energy calculated at the pole, right, is 0. Right? So this is one of the conditions I was looking for. And this one can be written, in fact, what I'm about to write also contains the first one, by saying that the full propagator behaves as I over p square minus m square when I go close to that pole, right? And in order to talk about the residue, what I can do is expand the full propagator, which is given by this analytical expression here, near the pole. I can go near the pole and do expansion for this guy. Let's expand the denominator first. So p square minus m square minus the self-energy is equal to, now I'm doing a series expansion on p square minus m square, right? As I go near the pole. The first term is just minus m square of p square calculated at this point. And I can see that from the first condition, this needs to be 0. So this is 0. The next term is 1 minus dm square p square over dp square at p square equal m square times p square minus m square. And of course you have higher order contributions, which are order p square minus m square square. Right? So the condition, if I substitute this, the leading contribution here, I put on this denominator, then I get the expansion for the full propagator, right? Which means I over p squared minus m squared minus the self-energy is approximately, as p squared goes to m squared, I over p squared minus m squared times 1 minus this thing, right? d m squared p squared d p squared minus 1, right? I'm bringing this to the numerator because these I can relate to the residue now, right? Essentially what I see if I compare these with the condition I have, this needs to be 1. So I'm getting that, of course, this is for p squared equal m squared. So what I'm seeing is that 1 minus the derivative of the self-energy in momentum square actually, but yeah, p squared equal m squared minus 1 needs to be 1, right? And that means, and this is the condition I was looking for, that the derivative in momentum square of m squared p squared, again, in that pole is equal to 0, right? Which is the second condition now explicitly implemented, right? I wanted information about delta z and delta m squared. So two variables, I have two conditions that should do it, right? Now to relate these explicitly again to delta z and delta m, I can go back to this equation, right? The conditions I'm finding are on this complete self-energy, and on the right here I have the pole contributions to the self-energy and the counter term contributions to the self-energy, right? So I will eliminate all the i's here. Let me copy this here. And take all these i's out. There's a minus here and a plus here, right? So I have this equation in which I can impose those conditions, right? So this is p squared. This is also a function of p squared, right? I was suppressing that notation, but it is useful now. So if I go near m squared, this needs to be 0, right? As per the first condition up here, right? And that means that these two terms need to be equal. So I get this condition p squared delta z minus delta m squared equal to these loop contributions, of course, calculated at p squared equal m squared. Keep in mind that delta z does not depend on momentum, as we said before, nor delta m, because delta m squared is a relation between m0, which is just a number in the Lagrangian, and the physical mass, which is again just a number. So these guys do not depend on momentum, right? And if I use this, if I take the derivative on p squared on both sides of this equation, I get that d m squared p squared d p squared is equal to minus delta z plus the derivative of the loop contributions to the self-energy in p squared, right? Which again, I can impose this condition on the left side, right? Which gives me 0, and then I get that delta z is the derivative of m square loop p square, the derivative in momentum square, right? These near this point. So these two conditions can be solved to get delta z and delta m, right? But the way we usually use these, right, is really looking at these equation here and this one, right? So I have to choose a form for delta z and delta m so that the contributions for the loop suffer a cancellation, right? This will be a polynomial in p square, right? And the linear and the first order polynomial in p square will cancel each other so that you get rid of all the terms that would violate the condition that when you go near p square equal m square, this is different from 0, right? So there will be a cancellation between counter terms and loop contributions of all the terms that could violate the condition that this is 0 near the pole. Same thing here, right? You can use this one or that one. If you solve this as a polynomial equation, you actually don't need the second one, but sometimes it's easier to use this second equation, right? And of course, now talking about infinities, right? Of course, if the loops are giving us divergences, right? Giving us infinities. Also, these counter terms will have to have the same infinities because they need to sum to a finite number. In this case, 0, but that's because of the particular renormalization scheme we have been using here implicitly, right? That's not the only option. I could have made some other choices here, and we'll see some of those choices in later. But for these choices, these need to add up to 0, but in any case, they will have to add up to some finite quantity because the mass, the physical mass needs to be finite, right? So that will get rid of the infinities, right, of the divergences, right? But the point I will make again, I know this is getting annoying already, is that I can imagine doing the normalization even if the loops are finite. If only just to have a theory which is defined in terms of the physical mass and not just some m0 that is related to the physical mass through a perturbative expansion, and you would have to redefine m0 for every order of perturbation that you calculate when comparing with the experiment. So defining the theory straight away in terms of the physical mass is much more useful, and we'll see even other advantages when we get to the renormalization of the interactions later, right? So you could think of that you would renormalize theories anyway, even without the infinities, but of course now you have the extra very important advantage of getting rid of these divergences, which we'll see in detail. I know saying that I have an equation here with a cancellation between divergent quantities summing up to give something finite can make some people nervous, especially after I did a perturbative expansion in delta z and delta m. So keep calm, right? We'll get to exactly what expansion I'm doing, right? The second point I want to call attention to here is that, as you see, these counter terms, delta z and delta m, are intrinsically linked to the loop contributions to the two-point propagator, right? In fact, there's no three-level contributions to the propagator, it's just the free propagator, right? That's one of the big advantages of doing calculations at tree level, is that the propagator is the same as in the free theory, right? Every next to leading order correction to propagators will be loops. And that means that also the counter terms only show up when you do loop corrections. So these counter terms are intrinsically connected to the loops in the theory. And as we said in quantum field theory 1, it's really on the loops that you get new effects from quantum field theory, right? Not just quantum mechanical effects. So you see, these guys will be very important and will have a lot of consequences for our theories, right? They're not just concealing infinities here. So keep that in mind too, right? I think that's all for the video today. See you on the next one.